Hello guys, we want to start lecture number 30. So in this lecture, I want to talk about half-range expansion. So you know that if we have one function defined on the range of minus p to p, for example, I have fx is a function which is defined on the range of minus p to p. In fact, we have a symmetrical range. So you know that the Fourier series of this function is a0 divided by 2 plus summation of an cosine n pi over px plus summation of bn sine n pi over px. And we already found a0, we found an, and we found bn. Now we want to see that if we have one function which is defined on the range of 0 to L, so what we have to do? In fact, the range of function is not symmetrical in this case. For example, see here, if y equal to fx is defined on the interval 0 to L, so here we have the function which is defined from 0 to L, we want to find Fourier series of this function. In order to find Fourier series of this function, we have three solutions, or we have three approaches to solve the problem. In the first one, we can reflect the graph that we have. So we can reflect graph of the function about the y-axis onto the range of minus L to 0. The function is even now, so you can easily find Fourier series of this function using the formula that we had in the past. So for example, here the blue function, the blue plot is it's graph of our function. Now we just reflected this function with respect to y. So now we have the red one in fact is reflection of the blue one with respect to y. Now in this range from minus L to L, which is a symmetrical range, so we have one even function, and for even function we can easily define cosine series. So in this case, p it's equal to L, and if you want to find Fourier series of function, because the function is even, so we have a0 divided by 2 plus summation of an cosine n pi over px, and n is from 1 to infinity because it's a Fourier series. It's a Fourier series of even function or cosine series. So in this case, a0 is equal to 2 over p. The integral from 0 to p fx dx, and an is equal to 2 over p integral from 0 to p fx cosine n pi over px dx. So it's the first solution for finding Fourier series of our function, which is the blue one. We just reflected with respect to y-axis. In the second solution, we can find reflection of the graph of the function through the origin onto a range of minus L to 0. So the function now is odd function. So if you get here, you can see the blue function is the original function that we have. We found reflection with respect to the origin. So now we have the red function. So the entire function from minus L to L is one odd function, and we can easily find Fourier series of odd function, which is sine series. So again, in this case, p is equal to L. So we have fx it's equal to summation of bn sine n pi over px, because function is odd, so n from 1 to infinity, and bn it's equal to 2 over p, the integral from 0 to p fx sine n pi over px. So here we could find Fourier series of function using sine series. In the third solution that we have, we can define fx on the range of minus L to 0 such that fx is equal to fx plus L. In fact, we have a periodic function. So in this case, we assume that P is equal to L over 2 and fx is equal to a0 divided by 2 plus summation of an cosine n pi over px plus summation of bn sine n pi over px. So n is from 1 to infinity, and here n is from 1 to infinity. So in this case, a0 is equal to 1 over p, the integral from 0 to L, not from p, so it's 0 to L, fx dx. An is equal to 1 over p, integral from 0 to L, fx cosine n pi over px dx. And finally, bn is 1 over p, the integral from 0 to L, fx sine n pi over px dx. So we can find Fourier transform of our given function using these three approaches. So you have to keep in mind that Fourier series of the function is estimation of function. It's something like this. If you use the cosine series, you will end up with something like that. It's the Fourier series of the cosine series. So you can see that in the range of 0 to L, we could find Fourier series, which is exactly what we found here. Or if you use the second approach, or you have sine series, so Fourier series of this function is like this. Again, so what is desired for us is Fourier series of function in the range of 0 to L, so we could find it. Or for the third case, if you find the Fourier series, you will end up with something like this. So again, we could find Fourier series of our original function in this range of 0 to L. So now we solve one example to see these three approaches more clear. In this example, we want to expand fx equal to cosine x. X is in the range of 0 to pi over 2 in a sine series, in a cosine series, and at the end, so we want to find the Fourier series. So here you can see the graph of function. So it's fx equal to cosine x, and it's in the range of 0 to pi over 2. First, you want to expand it using sine series. In sine series, in fact, we assume that we want to reflect our function with respect to origin, and we have one odd function. So if we reflect it with respect to origin, we have one odd function. So in this case, fx is equal to, we know that for odd function we have sine series, so it's a summation of bn sine n pi over px, n from 1 to infinity. So we said when we use the first solution or sine series, p is assumed to be equal to L. So here the function is defined on the range of 0 to pi over 2. So it means that L is equal to pi over 2. So it means that P is equal to pi over 2. So now we have to find Bn. Bn, it's equal. We have a odd function, so it's 2 over P, the integral from 0 to P, fx sine n pi over px, it's equal to, P is pi over 2, integral from 0 to pi over 2, fx is cosine x, sine n pi over px, it's n pi over 2 x dx. So if I just simplify it, we have 4 over pi, the integral from 0 to pi over 2, cosine x sine 2nx dx. So we can use the trigonometric equations to write cosine x times sine 2nx in terms of summation. So we have 4 over pi, so it's times half the integral from 0 to pi over 2, sine cosine a cosine b, it's sine a plus b plus sine a minus b. So we have sine x plus 2nx, so we have 2n plus 1x dx plus 4 pi times half the integral from 0 to pi over 2 sine to n minus 1 x dx. So as a result, Bn is equal to, so we have 4 over pi times half is going to be 2 over pi. Integral of sine 2n plus 1x is going to be minus 2n 1 over 2n plus 1 cosine 2n plus 1 x from 0 to pi over 2 plus 2 over pi minus 1 2n minus 1 cosine 2n minus 1 x from 0 to pi over 2. So it's equal to, so in fact Bn, it's equal to, I have to apply upper limit minus lower limit, so it's equal to 2 over pi. If I apply upper limit, we have minus 1 over 2n plus 1 cosine 2n plus 1 times pi over 2. And if I apply our lower limit, so we have cosine 0, which is 1, plus 2 over pi 1 over 2n minus 1. So here we have minus. I have to apply upper limit and lower limit. So if I apply upper limit, so we have cosine 2n minus 1 pi over 2. And if I apply lower limit, we have 1. So we could find Bn. So now we have Bn. You can easily plug it in this series and you can find Fourier series of this function. In fact, in this case, we have sine series. We assume that we reflected the function with respect to origin. If you see here we have the red one represent the Fourier series or sine series that we found, and the blue one is the original function. So it's fx equal to cosine x. As a result, in this range from 0 to L, we could find Fourier series of our function using sine search. In the second part, so the problem asked us to find Fourier series using cosine series. So in the cosine series, in fact, we have to reflect our function with respect to y-axis. So in this case, we have even function. So the Fourier series is equal to a0 divided by 2 plus summation of an cosine n pi over px. So n from 1 to infinity. At first, we have to find a0. So a0 is equal to, so we know that in this case, p again is equal to L, it's equal to pi over 2. So a0 is equal to 1 over p, the integral from 0 to p fx dx. It's equal to 1 over pi over 2, the integral from 0 to pi over 2. Fx is cosine x dx. So it means that a0 is equal to 2 over pi. Integral of cosine is sine, so it's sine x. The integral is 0 to pi over 2. So it's going to be 2 over pi. Now we have to find an. So an is equal to the 1 over p, the integral from 0 to p, fx cosine n pi over px. So it's 1 over pi over 2, integral from 0 to pi over 2. Fx is cosine x times cosine n pi over p. So p is pi over 2, so it's cosine 2nx dx. So you can easily find this integral as well. If you find this integral, now you have a0, you have an. So you can see that here the red one represents the Fourier series or cosine series. So here is Fourier series. And the blue one is our original function, which is cosine x, which is fx equal to cosine x. Again, in the range of 0 to L, we could find Fourier series of fx equal to cosine x. Now we go through the last part. So in the last part, so we have to expand the function in terms of Fourier series. In this case, is the third solution or third approach that we had. So in this case, we said p should be considered as L over 2. So it's equal to pi over 4. And fx is equal to a0 divided by 2 plus summation of, an cosine n pi over x, n pi over px plus summation of bn sine n pi over px. So n from 1 to infinity, from 1 to infinity. In this case, a0 is equal to 1 over p, the integral from 0 to L fx dx. It's equal to 1 over p. P is equal to pi over 4. The integral from 0 L, L is pi over 2. Fx is cosine x dx. An is equal to 1 over p, the integral from 0 to L, fx cosine n pi over px. So in fact is equal to 1 over pi over 4, the integral from 0 to pi over 2, fx is cosine x times cosine n pi over p is cosine 4 pi x sorry, for nx dx. So you can find an as well. So bn is the same, so it's equal to 1 over p, which is pi over 4. The integral from 0 to pi over 2, which is L. Fx is cosine x times sine n pi over px, which is sine 4 n pi x dx. So now you have a0, you have an, and you have bn. You can plug it in the Fourier series equation that we have, and you will end up with these plots. So in this case, the red one is the Fourier series again, and the blue one is cosine. So here, red one is the Fourier series, and the blue one is fx equal to cosine x. Again, in this range 0 to L, we could find Fourier series of our function. So you could see that it doesn't matter which approach you use. You can use Fourier series, you can use cosine series, you can use sine series to find Fourier series of cosine x in the range of 0 to L. Here you can see we had this function, the blue one. So here we wanted to find Fourier series of fx equal to cosine x in the range of 0 to pi over 2. At first, we said, okay, we can reflect our function with respect to origin here. So as a result, we have one odd function. And we could find Fourier series of odd function, which is a sine series. But what we have to look at is this range, because in the problem, it just asked us to find Fourier series in the range of 0 to L. The second solution, we assume that we can reflect function with respect to y-axis. So now we have one even function. We can find Fourier series of even function, which is a cosine series. And then we find it. So it's a red one. But again, what do you want? It's in the range of 0 to L. And in the third approach, we assume that we have a periodic function. And we found the Fourier series. So here we have Fourier series. And what is important for us is the range of 0 to L. So you can see that it doesn't matter which approach you use, you will end up with the same result in the desired range. It means that between 0 to L.